finish the support vector machines today. Consider support vector machines for regression also, and then move to ideas from Lasso, L1 regularization, with a hope by next Tuesday to finish the topic, and then we will see where we go after that. Okay, so what I'm going to do is I'm going to very briefly, since we went rapidly on the last short lecture on the case of SVM for data that they are not separable, so I want to basically go and provide a summary of the things we discussed. So when the data were separable, basically, at the end of the day, the optimization problem was looking like this. This was maximizing the margin or minimizing this magnitude of W. The margin was 1 over W. And at the same time, we had an error function. Equivalently, this is what we get. We had an error function that tries to enforce that for all data points, basically, this constraint is satisfied. And this constraint means that the data are separated exactly in future space. Okay? So this error function is with an argument z, it is equal to, if z is positive or 0, is 0, otherwise it's infinity. So basically, if something is misclassified, the penalty is infinite, okay? And so for linearly separable data, this is what we get. And by the way, I'm going to try to explore this type of formulation today, because if you pose support vector machines with some error function here, you can see similarities with logistic regression and other models in machine learning, right? So anyways, in the separable case, this is how the problem was looking like, and the function basically will assign infinite loss if a point is misclassified. All right, so we consider on Friday the case of data that we cannot separate basically in future space. And for those cases, we introduce slack variables xi. For each data point n, we introduce xn greater or equal to 0. And just let me summarize of the things we discussed. Xn equal to 0 for data points that they are on the correct side of the margin or on the margin boundary, as you see here. Xi less than 1 are points that they're on the wrong side of the of this margin boundary, but they are classified correctly. And then, if this is the separating hyperplane, we had Xi greater than 1, where points are basically are misclassified. So the idea here is to allow misclassification, because if you allow misclassification, even for separable data, maybe the predictive, the generalization capability of the model is better. In some sense, this xi is nothing else but the distance, basically, this distance of Tn from y at xn. All right, so it tells you how far you are from the margin boundary. Okay, so originally the constraint for correct classification was that Tn times y of xn greater or equal to 1. Now, since we allow misclassification, the constraint is Tn y of xn greater or equal to 1 minus xi1. Okay? And for the different values of the x's, you can get the 3 situations that I just mentioned. So basically, we need to set an optimization problem where the constraints take this form with additional variables now introduced that they are greater or equal to 0. Okay, so obviously we're going to try to maximize the margin or minimize W, and at the same time minimize this the misclassification, and that is measured in terms of the x's. So if you put some inverse regularization parameter C, the objective is find the x's and the W for a given C so that this thing is minimized. So we penalize basically linearly points that they are on the other side of this margin, right? Like this point and that point. This is what accounts for this. and at the same time we maximize the margin. And I remind you, the margin, it was 1 over the magnitude of W, so here what we do is we minimize. Okay? So 1 over C plays the role of regularization. If you think of this as a 2 regularization, you can see 1 over 2C is like lambda W squared, the way we have seen it earlier for similar things. Okay, so we want to minimize this. We want to satisfy this constraint where the x's are greater or equal to 0. So by now you know that the trick is to write down the Lagrangian for the problem. So we have the objective function. We're going to introduce, for every inequality, we're going to introduce a corresponding Lagrange multiplier. So we have n of those, so we're going to put an alpha n as a Lagrange multiplier times this constraint that you see here inside parentheses. And then we have C of n greater or equal to 0, so we're going to put another Lagrange multiplier to enforce that, so mu n times xn. All right, so effectively what we have is the constraint times a Lagrange multiplier. The only thing that you need to be very careful here, and I treat it as a well-known fact, you have to be very careful with the signs that you use in the context of enforcing these constraints, all right? You notice the way I have written them, there is a minus there, a minus there, and instead of minimizing, actually we're going to be maximizing with respect to alpha, okay? So again, if you want to read more, you can look in the appendices on books like Bishop's to see how Lagrange multipliers apply to this type of problems. So this looks a very complicated thing to do, right? And that's why sort of I want to go through this, because it's something very complicated is still very powerful, because it can lead to a nice quadratic programming problem that can be solved with more or less standard techniques. All right, so this is the Lagrangian. Now what you need to do is you need to write the optimality conditions, and the optimality conditions are the Kent-Tucker conditions. And I put here in blue the constraints that we had before, that they're part of these KT conditions, but also I put the additional 2 constraints that effectively say that the product of the Lagrange multiplier and the inequalities that you need to satisfy is equal to 0. So alpha n times this parenthesis equal to 0, and mu n times xn equal to 0. All right? So immediately you can see that, you know, either alpha n or this parenthesis has to be 0, and again here, either mu n or xn has to be equal to 0. So that's interesting, and hopefully will be the type of things we need to introduce sparsity in the model. So the first thing you need to do is, if you want to have a nice, clean quadratic programming problem, get rid of the primary variables that you started with, so you can write the dual formulation. So we're going to optimize with respect to W, take derivatives equal to 0, so you substitute, so it comes out that W is equal to that, right? W comes here, right? That's our model. You remember our model is W transpose phi plus beta, all right, inside the Y. So when you take derivatives with respect to W equal to 0, you get that. Derivatives with respect to B, and again, B comes inside here. It will be alpha n Tn equal to 0. And derivatives with respect to the variables C, and it gives you this interesting equation that says that the Lagrange multipliers alpha n equals C minus mu n. Okay? So effectively, in the Lagrangian that you see on the top, we can, with these 3 equations, we can get rid of W, we can get rid of B, we can get rid of C, and the whole problem becomes a problem in only in terms of Lagrange multipliers. That's the dual problem, and I think we already have seen this type of dual problems even when we discuss kernel methods in the context of regression. So if you do all the substitutions, and there is really nothing, it's you can literally look at these equations and here, and you will see that immediately you get this nice Lagrangian, okay? Everything is in terms of alpha, and you can see immediately This is a quadratic programming problem, but we have now to take care of constraints. And the constraints are obviously alpha n's, they have to be greater or equal to 0. Notice from this thing here, this mu n is a Lagrange multiplier. So mu n, which is c minus alpha n, has to be greater or equal to 0. So, so alpha n has to be less or equal to c. And then from one of these constraints, we had alpha n Tn equal to 0. So basically, you have a quadratic objective function with some linear constraints. This is a convex optimization problem. You can actually solve it and find a unique maximum here, right? This is what we are interested in terms of the alphas. And the only thing I'm going to say is solving this problem, if n is of the order of millions, right, which is typical on when you use support vector machines, this is not sort of a trivial, it's a black box sort of optimization, but it doesn't mean if you put n equal to million, every software is going to work, okay? So you need to do something very sophisticated. And you can appreciate here that to compute the alpha n's, you really have to use all the data points, right? The summation here is over all the n's. So everything has to be used, but when we do predictions, maybe things would be simplified. And I remind you the equation for prediction. Remember, for prediction, y is w transpose times phi of x plus b, and w is what? It's this. So when you have phi transpose times phi of x, you get the kernel function. So the prediction is given by this nice equation, and what we have to do is we have to discuss a little bit where the sparsity comes. Because here there is a summation in n, so the question is, are some of these alpha n's equal to 0? All right, so let me see with you here the algebra carefully. So remember, one of the KT conditions was alpha n times this constraint equal to 0. And alpha n has to be, for alpha n to be, if alpha n is greater than 0, all right? So this will be a support vector. If alpha n is greater than 0, this parenthesis has to be equal to 0. And if you look carefully, there are two possibilities for this to be equal to 0. And you can read everything here. So one of these possibilities will be a case that leads to points that lie in the margin, which are those two blue points. And there is the other possibilities for points that have either xi less than 1 or xi greater than 1, which are points within the margin that either they're correctly classified or misclassified. And again, all of these are derived from this equation. There are two cases. Alpha n is either less than c or alpha n equal to c. And following the KT constraints, you can see basically that this lead to either xn equal to 0 or xn less than 1 or xi greater than 1. Okay? So effectively, when you do predictions, the only points that contribute are these points with circles that you see here, that they are either points that are on the margin or inside the margin, okay, that are either correctly classified or misclassified. So the idea here is if you train the model, it can be a very expensive proposition, which can be quadratic in the number of points. You have basically done the most complex part of the analysis. Predictions are much simpler because the only points that you need to consider in making predictions for any x are the points, basically the support vectors that you see here. All right, and the last thing we have to discuss is how do you get the constant b, the bias term in the regression model. So what you do is you only consider the points that they are in the margin, so the points that xn equal to 0. So for those points, Tn times y of xn equal to 1, okay? And so I am expanding y of xn, and I write this, this is my prediction, and S is the set of the support vectors, because in this summation only the alphas that they are non-zero have to be accounted for. So then what you do is, instead of using this equation for 1.n that satisfies Xn equal to 0 and solve for B, what you do is you average over all the support vectors that satisfy Xn equal to 0. This is that set that you see here with calligraphic M. So when literally what you have to do is multiply by Tn and sum over all of these vectors, and then you get this nice equation. So that's a more stable estimate. Okay, there is an alternative formulation, and actually, if you go and you download from the web support vector machine software, a lot of the software follows this revised formulation that looks very similar, but the constraints and the objective function are a little bit different. So in the objective function, you basically have the quadratic term only, okay? And the constraints, some of the constraints look the same, but you notice there is a new parameter here that controls the model complexity, this parameter new, and the only thing I'm gonna say, so we don't get very technical, this parameter new basically bounds the fraction of the margin errors that you do, and the fraction of the support vectors. So it's sort of a parameter that controls the complexity of the model that you have to set in when, so effectively, rather than, saying something about the margin, you say something about nu in terms of the fraction of the support vectors that you want and the fraction of the margin errors. Apart from that, the optimization problem looks more or less the same. So here is some results using this modified support vector machine. And you notice here there is sparsity, but maybe not too much sparsity. All right, so this is a classification problem with Gaussian kernels with the parameter gamma here fixed. And if you try to do this with relevance vector machines, right, you will see that RVM does way better than support vector machines on this particular data set. All right. A little bit of, without reading any of the slides, how do you actually optimize this? How do you solve this large-scale optimization problems? All right. So the idea here is, obviously, we're going to use only the alphas that are related with support vectors. That's one thing. So the cost of the calculation will be squared to the number of support vectors, which can come to be a significant actually calculation. So there are implementations of this maximization problem where actually they use two alphas at a time, basically two support vectors. And these methods go under the name of chunking. So basically you divide the problem to a set of smaller optimization problems using literally at the end of the day two Lagrange multipliers at a time. And these algorithms, they go with the name linear scaling support vector machines. And I don't know if there is a proof that they work for all problems, but they're quite popular actually. So when you search on Google, the first thing you will get is linear scaling support vector machines. And you can consult some of these references. Again, these are maybe 15, 20 years old type of calculations. I don't believe anybody works anymore on support vector machines because the problem is done. But you need to know these things because if you develop some new method for classification, everybody will tell you, have you compared with SVM? There's no way to escape. Okay? All right. All right, I mentioned that the deficiency of SVM is that the method is not probabilistic. Okay, so it basically classifies these points. It doesn't provide you any probabilities. All right, it tells you if something is in one class or another, but it provides no probabilities. So if you want to make it probabilistic in some artificial manner, what you can do is you can take the output of a support vector machine classifier, this y of x, and with some coefficients a and b pass it through a sigmoid, and call this the posterior probability of x to belong to the class t equal to 1. Okay? And it comes out that actually this sort of can be a valid formulation if you interpret the answer that comes out of support vector machines as this log odds ratio that you see here. All right? So if the support vector machines basically simulates this, and then from this you solve for this probability, eventually what you get is something that looks like this. Okay? And I don't know if we said anything on this on Friday. Somehow, this probabilistic interpretation, because it's artificial, you can find lots of examples where basically the technique gives you garbage. And there is, in one of the papers by Tipping, there is an example of data generated with these two-class conditional distributions that they are uniform. So you have two classes. For one, the data are generated from a uniform distribution from 0 to 1. From another one, from a uniform distribution from 0.5 to 1.5. So if you look at this, if you take the priors of the two distributions to be the same, and you use Bayes' rule here, you can see on the common region from 0.5 to 1, from 0.5 to 1, these two probabilities will be the same. So you get log of 1, which is supposed to be exactly 0, and away from this region, this log odds ratio is supposed to be infinity. So basically, this is the exact answer, and you can see the support vector machines from data generated from these two conditions looks way out of reality. Okay, so in this particular problem, it's a man-made example. Support vector machines fails to give you anything that looks probabilistic in nature. All right. So we discuss support vector machines for classification, and the question then is, how is this relates, with probabilistic methods that we have seen for doing classification, and in particular, how does it relate with probabilistic estimates we got for logistic regression? So let's see what is going on here. So I remind you, the objective function that we minimized was this. You remember? So this objective function, right? I remind you, xi was 1 minus y times t, all right, for each point n, okay? And this objective function that we get here, in terms of y1 tn, is what is called the hinge error function, which is, I define it here, all right? So this basically picks up only the positive part of this function, and the positive part is really the xi's. So the formulation that you see here, and using the hinge error function, they're the same thing. So if you want to pose the support vector machines as an optimization problem, you can write it directly as minimize this error, where the loss for each point is defined in terms of the hinge error function, definition here, plus some regularization, minimizing the norm of W squared. So why am I referring to this? Because effectively, if you have the hinge loss function, maybe other methods, including logistic regression trained with maximum likelihood, maybe can take some form that looks similar to that. So we need to investigate on how things look like with standard probabilistic methods. So before I show you what you get with logistic regression, let me give you a plot of different error functions. So these are error functions as a function of z. This is z, and really z here refers to y times tn. All right, so yn times tn. So this Hinz error function is basically this blue function that you see here, and it is really this plateau here of zeros that gives you, the sparsity in the model. All right. This is a quadratic error function that we have seen before for regression, and obviously it's not going to be working well. This is the misclassification error. Remember the misclassification error, if y and t have the same sign, right? So if y is positive, t is positive, the error is 0. If you have the opposite sign, then the error is 1. All right? So if you classify correctly, there is no loss. Otherwise, the loss is equal to 1. So effectively, these error functions that you see in this plot, and I'm going to come back to this error function for the logistic regression, they are really trying to do nothing else but approximate the misclassification error. Okay? So let me see. So this is what you get with support vector machines, this blue line. So the question is there anything we have seen already that somehow is an approximation where this blue line is an approximation to things we already have seen? And the answer is yes. So let's revisit logistic regression. You remember in logistic regression, this is the whole model. You try to model the posterior probability of t to be equal to 1 as a sigmoid defined at this function. Right? So you do a linear model, you pass it through a sigmoid to get probability, and you set it directly, and you say, that's the probability for the next. All right, that's the probability. Now, if you try to calculate the probability for the label to be -1, it comes out, you get 1 minus sigma y, right? So this probability would be 1 minus the probability of t being equal to 1. And 1 minus sigma of y, you can show that is sigma of minus y. So I can write actually for both this equation and this equation, I can write them simultaneously as the probability of t given y to be sigma of yt, of the product of sigma of yt. I mean, if t is +1, right, I get the probability of t being 1 is sigma of y, which is what I have here. If t is -1, I get sigma of minus y, which is 1 minus sigma of y, so I'm correct. So this is a compact way to write, if you like, the likelihood of the logistics, logistic regression model. So if you try to maximize, to maximize the likelihood, it will be the same as minimizing the minus log likelihood. All right? So if you take minus log likelihood, you remember what's the sigmoid? How does the sigmoid function look like? What's the equation for the sigmoid? Is 1 divided by 1 plus e to the minus yt, right? So when you take logs of that, you will get minus log of 1 plus e to the minus yt. So when you take minus the log likelihood, so we can plug it in here as a in the loss function that we want to minimize, what you get is you get a loss function that is log of 1 plus e to the minus yt. So if you scale this properly, the logistic regression function is this red curve that you see here. So actually you can see that with this setting, the support vector machines, this Hinz function that we get, it's nothing else but it's sort of an approximation to what we get with logistic regression. In logistic regression, you don't get any sparsity. Here we get a sparsity because when yt is greater than 1, this loss is equal to 0. And this is what results in the sparsity. Okay? So logistic regression is the straight line, and the Hinz function is the blue line. Okay, so the slide basically has the same thing and a little program from Murphy's book if you want to see how these functions look like. And all right, so these are things we already have seen. There's nothing new there. Nothing new there. Okay. So if you want to take things to the extreme, right, and you're asking yourself, can I actually do some probabilistic model better than what I showed you before with passing an SVM output through a sigmoid? Can I do something better? And so people use their imagination to come up with different models, and I only just wanted to show you one equation. So you remember the error function that we minimize is this hinge error function, right? This is what we get with support vector machines. So somebody observed the following interesting thing, that if you take the exponential of this with just some scaling coefficient 2 that is unimportant here, you can actually write this exponential as this integral in some parameter space lambda, all right, where lambda comes, as you see here, as if it was the variance of a Gaussian. And so the person who got this nice integral said, wait a second, if I can write, all right, if I can write this as an integral in lambda, maybe what I can do is I can treat lambda as a hidden variable, and I can actually train the model iteratively using expectation maximization. And people wrote papers on this, okay? Just simply using this nice formula. All right? So you can do lots of fancy things if you're interested, and some of the papers that you see are written there. Okay, so let me, I'm going to jump now. Oh, I actually need to tell you something on, so you remember, so when we wrote the objective function, right? There was a regularization parameter C, right? This is not a probabilistic method, so this parameter C controls the complexity of the model, and the question is, how do you get this parameter C? And it comes out that it's not trivial, because not only you have to compute C, but you have, you use kernels, right? And if you use kernels like a Gaussian kernel, you're going to have to compute the width of the Gaussian kernel, right? So, for example, here is for a Gaussian kernel, you can think, if you take it a Gaussian, you can think of gamma 1 over 2 sigma squared to be sort of the width of the kernel. So it comes out that computing C and the parameters in the kernels, they are not two independent problems, and the two things are highly related. So if gamma is a big, if you select for the precision in the kernel a high number, then C has to be very small. If gamma is a small number, C has to be very big. And so what people do is they do cross-validation. And in the cross-validation, actually, you have to play with many parameters C that you need to test your model simultaneously for all possible gamma values. So we're talking about heavy-duty type of simulations, but maybe you do this over a small data set, right? You don't do this on a huge data set to test this. And there is an idea that allows you sort of to compute the cross-validation error for all combinations by doing what is called a path-following algorithm. And if we have time, we will discuss this in the context of another algorithm that is related to lasso that is called Lars. So the idea here is to start with a very high regularization parameter, then slowly start reducing the regularization parameter. And what that results with zero support vectors when you have very high regularization, and then eventually, I'm sorry, you start with, so when lambda is high, all points are inside the margin, all right, so there are support vectors, and as you reduce lambda, basically all points are removed out of the support vector set, And so you can do these calculations efficiently using an idea that is very similar to large. So if we have time, we will discuss this next week, okay, in the context of the Lasso algorithm. I'm going to bypass this. There is nothing new really on this topic. So I'm going to go to on how do we use support vector machines to do regression? Is that possible? Right, because everybody, when they think of classification, they think support vector machines cannot do regression. So let's see what, so our standard non-probabilistic regression problem, right, that we saw very early on in the course, this using MLE estimates and with regularization like a map estimate with a Gaussian prior, was basically to minimize the response of the model from the target values plus the regularization parameter. So here is what's the idea. We're going to introduce what is called an epsilon insensitive error function. So we are going to postulate that if the difference between y and t is smaller than epsilon, we're going to assign zero error. We're going to say that's not, it's okay. The cost, basically the loss function, if y minus t is less than epsilon, is zero, and we're only going to account for errors above that level. So we're going to define an error function. We're going to modify this, and we're going to say if t is within a cube of size epsilon around y, the error is zero. Otherwise, the difference of the two will give me the error. So effectively, you can think this is the function y, this is the regression function, and we're going to assume that the errors within this cube of size epsilon are basically zero. Okay? So we're going to modify the error function to look like this. Now you may say, and so what? Why is this going to allow me to come up with a sparse model, right? And obviously, there is a lot of ingenuity here to sort of start on this and see immediately that it's going to lead to a sparse model. So what they have done is they have introduced two slack variables to allow points to be outside this epsilon cube. So points basically can be on the top of this cube, and we're going to assign a slack variable c greater than 0, and then points can be below that cube, and we're going to assign the variable c hat. And you can see basically, so c hat, xn for a point n corresponds to points for which Tn is greater than y of xn plus epsilon. So if you take for a given location, are points basically on the top of the cube. And Xn hat are basically points that they're below of y of xn minus epsilon. Okay? So effectively, we're going to modify the error function the way that you see here. So what's the meaning of this term now? So these points are points that they are above the cube, and these are points that they're below the cube. So what do they account for? So when we say minimize this error function, what does the first term minimizes? Remember that any point that inside the cube, we assign zero loss. And only the points above and below are going to have a loss. And how much that loss is going to be? For the points above is xn, for the points below is xn hat. Okay? So, and again, these are the points above, these are the points below, and this is the loss function coming from these two inequalities, if you like, and again, we want to minimize W exactly as before. So we have two inequalities.
we will need two Lagrange multipliers, alpha n for the points above, the cube alpha n hat for the points below, and why there's a need for two additional multipliers here. Why do I need, so I can see here I have alpha n and alpha n hat for these 2 points. Why do I need mu n and mu n hat? Remember, we need one Lagrange multiplier for every inequality. So what are the 2 other inequalities that need to have their own Lagrange multipliers? Where the 2 Lagrange multipliers come here? You can see in the equation below. Why do I need a Lagrange multiplier mu n greater or equal to 0? It enforces what inequality? You remember Xn, the slack variables Xn and Xn hat are greater or equal to 0. So someone needs to enforce those, right? Because they're primary variables, so they're going to be enforced with Lagrange multipliers mu n and Lagrange multipliers mu n hat. So effectively, a regression problem, it takes a very similar form to these support vector machines we have seen for regression. We want to minimize this minus these constraints here that enforce the positivity of the x's, and then minus alpha times these 2 constraints for points above the epsilon cube and for points below the epsilon cube. Okay? The rest is the same as for classification. What you need to do is get rid of the primary variables. So get rid of W, get rid of the Xn and the Xi hat, okay? And write things in terms of the Lagrange multipliers, alpha, alpha hat, mu and mu hat. And when you take derivatives, straightforward algebra, if you have done one of these problems, all of them work exactly the same. So if you take derivatives with respect to W, you write this. With respect to B, you write this. With respect to Xi and with respect to Xi hat. And you plug them in. The objective function now becomes an objective function only in terms of the alphas. All right? And the constraints now in terms of the alphas are these box constraints that alpha n has to be less than C and alpha n hat has to be less or equal to C. This has to be satisfied. And alpha n and alpha n hat, this constraint should remove, it's already there, okay? All right, and when you do predictions, you can use this equation, right? So for every x, your answer is W transpose phi of x plus B. So when you plug in the W transpose, so you're gonna have phi transpose of xn times phi of x. So it will give you a kernel function. And then the question is, and where is the sparsity? So can you start thinking on why is this a sparse model? I mean, we started with this stupid idea of an epsilon insensitive cube, and somehow we have been told that this leads to sparsity. Where is the sparsity? To look for the sparsity, what do we have to look in this equation? We need to look for which points n these things are non-zero, right? We have to figure out, are all the alpha n's and alpha n hats non-zero? Because if all of them are non-zero, then there is no sparsity induced when we do predictions. All right, so what I have done here is I have written the relevant KT conditions. All right, alpha n enforces this constraint equal to 0, alpha n hat enforces this equal to 0. Here, I remind you, it was mu n, Cn equal to 0, but mu n, we derive it to be C minus alpha n. This to be C minus alpha n hat, Cn hat equal to 0. So let's see what's going on. for alpha n to be non-zero, we need to have this whole parenthesis equal to 0. Correct? So look now at this whole parenthesis equal to 0. So for this to be true, what needs to happen? Remember that yn minus tn, right? I'm sorry, yn plus epsilon minus tn is a point where? We have a cube, right? You can see this is y, all right? So for a given x, all right, this is y plus epsilon, all right? Y plus epsilon, and any point that is above that is y plus epsilon plus xi. So according to this equation, the point Tn has to be where? For this equation to be true, what needs to happen? Either the point Tn is going to be on the boundary of this epsilon insensitive cube, and on the boundary xi is equal to 0, or it has to be above. Can you see that? Either xi is equal to 0, which means the point n is on the boundary of this epsilon cube, or xi is greater than 0, which means point n is above the cube. All right? So to get a support for the point n to give us a non-zero alpha n, all right, we need to either have points on the epsilon cube or above the epsilon cube. All right? Similarly, if you use this, it comes out that for this to be to be positive, basically, this has to be equal to 0, and that leads to either xi and hat to be on the bound to be equal to 0, so the point n to be on the boundary, on the lower boundary of the epsilon cube, or it has to be below. All right? So this is the only way for alpha n and alpha n hat to be 0, to be positive. But here is a problem. If you take alpha n to be positive and alpha n hat to be positive, so we have this equal to 0, this equal to 0, the two parentheses. So if you look carefully, this is inconsistent. So if you look, this is equal to 0, and this is equal to 0, what happens when you add them? You're going to get 2 epsilon plus xi hat, y and t cancel out, right? If I have the correct signs, minus y plus t. So, and this is positive, epsilon is positive. So what does that mean? That this cannot be equal to 0. So you cannot have both parentheses that you see here equal to 0, which means you cannot have simultaneously both alpha n and alpha n hat to be positive. Does it make sense? I mean, we said here for this to be positive, this has to be equal to 0. For alpha n hat to be positive, this has to be equal to 0. All right? But if both alphas and alpha hat are positive, so the both parentheses are 0, it's inconsistent, it's wrong. So what's the conclusion here? The support vectors here are points for which either this is non-zero or that is non-zero. Okay? So these are points basically as either on the boundary of the tube or above or below the tube. Okay? And you notice here, don't treat this tube as a margin, because now we are looking for points that they are either on the epsilon cube or above or below the tube. So the sparsity comes from a different direction, if you like, because it involves points that they're outside this tube. If you select a particular set of points for which xi equal to 0, so points basically that they're either on the upper side of the tube or below, For those points, you can use this constraint from here, and then you can solve for B. And if you want to get a much better estimate of B, what you can do is you can average over all these points N that satisfy these constraints, and you can get a stable estimate for B as well. All right, and so here is a little example of doing regression on using support vector machines. If nothing else, right, it's very interesting because you look at this and immediately you can see how different things are from a Bayesian setting, or in a Bayesian setting, somebody will look and say, well, are these your error bars? No, they're not the error bars, because this epsilon thing here has been preset, okay? And you see the support vectors are points that they're either on the boundary or on the top or on the bottom of this epsilon cube boundary. So, so if nothing else, right, this is a way with support vector machines to do regression. I'm not quite sure if anybody will ever ask you to compare anything in the context of regression with support vector machines. And I'm actually, I'm very doubtful that anybody has actually used this for any high dimensional problems. So most probably these techniques don't work on high dimensionality problems. Okay. There is something about, so back in the 80s and 90s, you know, most of the people in computer science, they were basically theoreticians working on what's called statistical learning theory. So support vector machines basically was developed using statistical learning theory. And in statistical learning theory, basically, there are two pertinent questions that seem we don't anymore ask because maybe we don't have answers. But the two questions are, how large a data set needs to be to allow you to have good generalization, right? And then can you compute some bounds on the cost of learning, okay? And you can, there is 2 or 3 slides with a bunch of references if you want to look more at this. The only thing I'm going to say, nobody's using actually these ideas anymore because the estimate of the number of the data that you need to have good generalization and the bounds for the cost of learning are really extremely conservative estimates. So it's like, you don't even know if they are 1,000 times higher. It's like somebody telling you, this is bounded from infinity, all right? So still, you know, the foundations basically of machine learning was way more rigorous back in the 70s and 80s because in a Bayesian setting, we cannot even have conservative bounds, right? We cannot say very much, but in statistical learning theory, this was a primary focus, if you like. All right, so let me do the, so we can keep moving on this. So let me, try to start moving forward with the sparse models. So on Tuesday we can, not on Tuesday, on Thursday we can discuss about lasso algorithms. So again, we are looking basically for generalized linear models, and we're trying to pose the questions, can we make them in such a way that you know, some of these W's basically disappear when we do predictions, both in the context of classification and regression. And I mean, this is an essential problem, both in the case where you have very high dimensionality and a few data. So, you know, if you have many futures, the question is, do you need all of those, or some of them are irrelevant in doing predictions? And we, you know, sort of we pose these things with variable selection. We discuss regression problems. So we will revisit some of these techniques in the next 2 or 3 lectures. But also we have seen this in the context, in the opposite case, where n is very large, and where we use basis functions that they're centered around each data point using kernels. So if your future space looks like this, and n is huge, all right, do you actually need all of this? All right? Can we find a subset of the training data to use for predictions? The only thing I'm going to say that in the last maybe 10 years, feature selection and sparsity is one of the most active areas in machine learning, in communities, that work in signal processing, uncertainty quantification, and you say it. So this is sort of an extremely relevant problem in machine learning. All right, so let me give you one example. So I'm going to define some binary variables. And so imagine that we have d futures, and gamma j defines if future j is relevant to predictions. So when gamma j equal to 1, it's relevant, otherwise it's irrelevant. And we're going to use a Bayesian framework. So we're going to assume that we can write a likelihood model. So we have some observations. So a likelihood model of the probability of observations if we knew what is relevant and what is not, plus some prior model for gamma. Okay? And effectively, we're going to ask, can we compute the posterior of this binary vector gamma given some data set D? And I have written this in a very compact way here that maybe look weird. Notice there is a log here and there is an exponential there. So can you guess why somebody will write something like that? What type of function is this? Softmax, okay? So, you immediately see sort of, you can take a very generic calculation of the posterior of this futures gamma, and you can write this posterior function as a softmax probability, right? So we're going to try to do this type of things for regression and classification problems and see if this type of quantities can be computed. You can appreciate if you have more than 10 futures, trying to do this calculation is mission impossible. And if I remember, for those who took the class in the fall, you did have to do a calculation of this distribution. You remember where? In the homework. Where did you have to calculate a posterior over futures? And actually you did not really, you did two things. Either you evaluated this for all possible models, or in addition, you sample from this distribution using Markov chain Monte Carlo. You remember the example? Which was your favorite example in regression? What data set problem was that? You see why I can give the same problem twice, right? It would be new to you. How about, did we do this in the caterpillar data example? Yes? No? You did not have to compute this probability and do calculations and sample and show the posterior for different models and which model was most possible? Yes? No? All right. Okay, perhaps. All right. So, so here is an example to just get an idea of the complexity of this, right? So we have a standard linear regression model defined by this simple equation. All right. There is no. We work directly with x, so there's no phi of x here. And what we do is we generate data artificially using a W that has some sparsity on it. So we pre-select, right, and we say, let's pick sigma square equal to 1, And let's use W to be given by like this. And let's take samples basically for different x's calculated y's. And then somehow try to go on a reverse and see, can we actually discover that the W here was a sparse model? How easy would that be, that problem, you think? So we start generating data from a regression model that we have, as you see, 1, 2, 3, 4, 5 variables are not there, all right? And then once we generate the model, how easy will it be to find out that 5 variables were not there? I mean, how many models totally we have on this case, right? We have how many variables? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many models we have totally? How many models? Every variable is either in the model or it's not. So what's the total number of models? 2 to the 10th, all right? So we have 2 to the 10th, and it may sound, that's why I mentioned the caterpillar problem, because you may actually literally went and calculated, and it was more than 10 variables there. It was like 16 or something, okay? So if you go and you enumerate this, right, you are going to get basically all the posteriors, and then you will see which model has the highest posterior. But even then, do you really believe that you will actually identify where the sparsity came from? What variables were not there? So the answer is no. This is a very difficult problem, all right? So if you, so the true model is the model that the variables 2, 3, 6, 8, and 9 are there, okay? And so when you calculate explicitly this posterior for overall possible models, what you actually get is, you get results that look like that. So the most, this is, if you enumerate the models, this is the model number 4, comes with the highest probability, and it includes only the, the second variable. This other model includes the second and the sixth. By the way, you can see all the models here include the second. And then as you go down with lower posterior probabilities, this includes 6. Obviously, this has low probability, but includes 6 and 3, but not 9. That's very weird, all right? And then suddenly this includes 5, but doesn't include 3 or 6, etc. So how are you going to be able to actually, so you cannot actually extract the truth from this calculation. So when you compute this posterior over models, it fails to recognize the true sparsity in your model. So so this is actually a very wonderful plot, all right, that you should do, to demonstrate how your algorithm explores sparsity. So in this case, we have 1,024 models. So the horizontal axis is all the possible models. And what do you think is the vertical axis, black or white? For each variable, what do we show on the vertical axis? We show which variables are in or out, okay? So this is a standard way to show for all models the sparsity. And what I want to concentrate here is, so I show you this posterior probability over models. So these are the 1,024 models, and you can see with some scale effects, some models have very high posterior probability, other models basically have 0 or very small, but immediately you can appreciate that somehow we capture some sparsity in the model. And this plot is a little bit better, because this plot gives you the posterior marginals of gamma j's. So it doesn't give you the posterior over models, it gives you the posterior marginal of every variable gamma, all right? And you can see immediately that variable 2 has the highest marginal. Not surprised, because 2 belongs everywhere. And then you can see variable 6 has the second highest marginal. Where is it? All right, 6 has the second highest marginal. And then variable 9 has the third. marginal 9 has the third highest marginal. So the idea then may be, should we, instead of computing this posterior over modulus, compute the posterior over this marginal posteriors? And you can do this, and you can actually, what you can do is, you can postulate and say, find, let's say, the j variables for which these posterior margins are greater than 0.5 or some given value. All right? So maybe you can say any variable that has a posterior marginal greater than 0.5 has to be in the model. This will fail because look at this, right? If your criterion is that every gamma that has a posterior marginal above 0.5, it's in the model. So which variables, according to this plot, are in the model? Obviously variable 2, and what else? And variable 6. So you're going to say, okay, maybe this is, not, I'm asking too much, right? Saying, finally, this probability greater than 50% is too much. Maybe you can reduce the 0.5 to, let's say, I don't know, to what it says here, 0.2 or something, 0.1, okay? So if you reduce this to 0.1, which other additional variables do you incorporate? It would be the variable 3 and the variable 9, right? Is the variable 3 and 9 in the true model? 3 and 9, they're in the true model, all right? And so we had 2 and 6. And see what happens next. If you reduce it even further down, something like that, okay, you need to capture this variable 8 that's in the model. But you know what? Before you capture the variable 8 using these marginals, which other variables are going to be artificially in the model when they don't belong there? Like 7. 7 doesn't belong in the model, but has a posterior marginal that is higher than the variable 8. So the bottom line is here, right, that any way you do it, there is a high chance that you may not be able to discover the truth sparsity in your model. Okay, that's a very difficult problem, and it's a problem of ongoing research. Now, we're not going to do it in these lectures. We don't have time, right? But you can imagine that if somehow you create sort of some random walks over models, you can get an estimate of these probabilities depending on how many times you pass through a given model, okay? And hopefully if you do many times, that will give you a reasonable approximation of the truth, but again, there are no guarantees of any type. All right, so let me, since we talk about regression and sparsity, let me introduce some prior models for gamma and see how we can induce sparsity on this, okay? So we have 6 minutes, so let's try to, so what I have done here is I write the posterior of gamma, given the data, as the prior times the likelihood, and remember the W's and the sigma squares are integrated out, so this is a marginal likelihood, okay? So I can only see gamma and my data D. So we're going to introduce a prior model on gamma, and I'm going to use I'm going to take all the futures, all the directions, if you like, to be independent. And I'm going to use P0 for a future being relevant, and 1 minus P0, the probability of not being relevant. So this gamma 0 here, this norm, what does it do? What is gamma 0? What does it capture? When you see summation of gamma j's, right, that's the 0 norm, what is that capturing? The number of non-zero elements that I have in the gamma, so it's the effective parameters in the model. Okay? So this norm captures the effective parameters, and pi 0 is the probability that f future is relevant, and I take this to be the same for all futures j. So you can write this, if you take logs, this prior model, you can write this this norm times log of pi 0, this log of that. And you can write this. There is a constant here. Pi 0 is fixed. And I can write this minus lambda, that is the log of 1 minus pi 0 over pi 0 times gamma 0. So basically, I would like to use this form in the next few slides. So the prior is written as the 0 norm of gamma, all right, times some parameter lambda that is defined as log of 1 minus pi 0 over pi 0. Okay, let's see where this thing goes. So to be able to do this calculation, you're going to have to find this marginal likelihood, which is complicated, right? So the marginal likelihood, how do we get it? To get the likelihood of the data for the observations for the input X, you can only do this if you knew W and gamma. So it means you need to know which parameters are in, and for those variables that they are in, you need to know what the W is, what's the coefficient in the regression model. Then you're going to need to use your prior on W and the prior sigma square, and then integrate W sigma square out, right? So given gamma, we're going to have to perform this, which means we're going to need the prior on sigma square, and we're going to need the prior on W. So the model that we're going to start towards these lasso algorithms is what's called the spike and slab model, and is defined basically by this nice equation on the bottom. So I want you to look carefully and get me a sense of what this model does. If gamma j equal to 0 means what? According to our definition of gamma, means that the j future is not in the model. If it's not in the model, the corresponding W goes to where? Becomes a delta function centered at 0, right? Okay, and if the future gamma j, if the future j is in the model, then I take the prior on W to be sort of a Gaussian model similar to what we had before. And you may say, why do I call this, of course, a spike, right, and a slab? Because if you take this normalization noise level sigma W to go to infinity, you can see that this Gaussian becomes basically a uniform distribution, right? It's an approximation of a uniform distribution, which goes with the name of slab, okay? So this is not necessarily a desirable model, because effectively you are asking to play with two priors. One of them is a delta function, another one is a Gaussian. And this may create problems when you do calculations, but sort of it's a primitive model to explore sparsity, all right? And it looks like this. So, so if we, so what have I done on the equation on the top, you think? What does the subscript now gamma in the equation on the top on every variable implies? And again, for those who have taken the course last fall, we already have seen this, but there is nothing new, right? So before, I had a model that looks like that, given gamma. So now, I don't see a gamma explicitly, but I see a subscript gamma. So what exactly is going on here? I have simplified the previous equation, and how did I simplify it? If I knew gamma, I would know which axis I should keep, right? Because some of the futures are not going to be needed. Similarly, if I knew gamma, I will not keep all the W's. I will only keep the W's with indices gamma that they're equal to 1. So what does the index gamma here mean? W gamma, ID gamma, what does it mean? It only includes the futures that are present in the model. So if I knew gamma, I would get rid of all the variables that don't belong to the model. And I use the same symbols as before. I just put a subscript gamma to say, for the variables that they are in the model, right? let's note instead of x now I'm going to have x gamma. Instead of my whole vector w, have only w gamma. So if you have, let's say, w1, w2, w3, and w2 is not in the model, then w gamma is w1, w3. All right? So this is the prior now on the w's that stay in the model if I knew gamma. All right? And you remember, these w's will disappear, and the only w's will be coming from this Gaussian. And that's exactly what I have here. But you notice I put this identity matrix here to account for which variables are in the model. I can generalize this, all right? And instead of using the simple thing with this Gaussian here, I can put a generalized covariance that looks like that. And I can see the time is going to be off in 1 second. I can write the marginal likelihood with this nice Gaussian here, okay? So what we will do is we will try to start with this model and see how we can expand it in exploring sparsity and move basically from this type of regularization to L1 regularization, which is lasso. Okay? Read the slides, please, because there's a lot of slides, and I'm not going to be able to cover everything, so I want you to see some of the intermediate details. Okay? So we'll pick it up from this slide 14 on Thursday.